Suppose we have a unitary operator u and a discrete set of gets, let's say x1, x2 till xn. Since u is a unitary operation, it is continuous. In order to make this point clear, we can represent u in terms of an exponential function u equal to e raised to I h, where h is an Hermitian operator. And since an exponential function is continuous, u is also considered to be a continuous operator. Since u is a continuous operator, we cannot represent it in a set of discrete gates. Rather, we can use this discrete set of gates to approximate the unitary operator u. So in order to understand this, suppose u and v are two unitary operators, where u is the target unitary operator and v is the actual unitary operator implemented in practice. We define the error when v is implemented instead of u as e uv equal to max of the state psi of the norm u minus v operated on the state psi. Here the maximum is over all normalized quantum state psi in the state space. Now if EUV is small, then any measurement performed on the state v psi will give approximately the same measurement statistic as a measurement of u psi. So in our topic of approximating unitary operators, we define two statements. First one is for a measurement operator m in the POVM element, if PU and PV are the probabilities of obtaining this measurement outcome, if U or V is operated, then the magnitude of PU minus PV would be lesser than equal to twice the error function EUV. And if the error function E is small, then the probabilities are mostly similar. Secondly, if we perform a sequence of gates V1, V2 till Vn intended to approximate some other sequence of gate U1, U2 till then the error at most linearly. That is, the error operator E would be lesser than equal to j1 to n e uj vj, which implies that our error is lesser or equal to the sum of the individual errors corresponding to these sequences. In order to prove the first point, suppose a quantum system starts in the state psi and we perform either unitary operator u or v. Following this, we perform a measurement and let m be a POVM element associated with the measurement. Also, let pu and pv be the probability of obtaining the corresponding measurement outcome if the operation u or v was performed. Then we can say that pu would be equal to psi u dagger m u psi and pv would be equal to rho of psi v dagger m v psi. We also define delta stat equal to u minus v operated on the state psi, which implies the bra of the delta state would be equal to bra of psi operated by u dagger minus v dagger. Knowing this, we can write the mod of pu minus pv equal to bra of psi u dagger m u ket of psi minus bra of psi v dagger m v ket of psi. Now what we will do is, we have added and subtracted these two terms such that we can combine these two terms and these two terms. This would be equal to bra of psi u dagger m taking common u minus v and bra of psi again taking mv common u dagger minus v dagger mv into ket of psi. Now u minus v ket of psi is our delta state and bra of psi u dagger minus v dagger is also bra of delta, which would be equal to bra of psi u dagger m delta plus delta mv psi. So we have written the mod of pu minus pv equal to bra of psi u dagger m delta plus bra of delta mv ket of psi. Now this term would obviously be lesser than the mod of psi u dagger m delta plus the mod of delta mv psi. This comes from the triangle inequality, and using the Cauchy-Schwarz inequality, which says that mod of the phi psi would be lesser than norm of phi into norm of psi. Therefore, mod of psi u dagger m delta would be lesser or equal to norm of mu psi into norm of delta, and delta mv psi would be lesser than or equal to norm of delta into norm of mv psi. And since m is the measurement element and u and v are the unitary operators, the norm of mu psi and norm of mv psi would be always lesser than or equal to 1, which implies this value would be always lesser than or equal to norm of delta, and this value will also be equal to lesser than or equal to norm of delta state. Therefore, we can write the mod of pu minus pv lesser than or equal to twice the norm of delta state, and our delta state is nothing but a error function EUV. So we can say that the mod of PU minus PV would be lesser than or equal to twice the error function EUV. So we proved the first point. Now let's try to prove the second point, which talks about the linearity of our error function E. Suppose we perform a sequence of V1, V2, Vm of gates intended to approximate some other sequence of gate U1, U2, Um. Then it turns out that the error caused by the entire sequence of imperfect gates is at most the sum of the error in the individual gates. That is E Um minus 1 till U1 and Vm minus 1 till V1 would be lesser than or equal to the sum of the individual errors caused by minus 1, Vm minus 1, which can be written as sum of j1 to m e uj vj. To prove this, we start with the case where m is equal to 2. Therefore, e would be a function of u2, u1, v2, v1, which would be equal to norm of u2, u1 minus v2, v1 operated on psi. This would be equal to norm of u2, u1 minus v2, u1 plus v2, u1 minus v2, v1, where we have added and subtracted v2, u1 operated on the state psi. Now using the triangle inequality, which says that norm of A state plus B state is lesser than or equal to norm of A state plus norm of B state, we can say that E u2 u1 v2 v1 is lesser than or equal to u2 minus v2 u1 psi plus norm of v2 into u1 minus u2 v1 into psi. Now we know any unitary operation does not change the norm. That is, norm of u operating on the state psi would be equal to norm of the state psi dash, where psi is almost approximately equal to psi dash, which implies norm of u2 minus v2 into u1 operated on the state psi will be equal to u2 minus v2 into state psi dash, and this norm is exactly the error E u2 v2 in approximating u2 by v2. Similarly, norm of v2 u1 minus v1 psi would be equal to the error due to u1 and v1. Therefore, we can say that the error function for u2 u1 v2 v1 is lesser than equal to the sum of the individual error function caused due to u2 v2 plus u1 v1, and this result follows the general case with m gates. So I hope you understood how we can approximate unitary operators and the error that occurs during this approximation methods.